What existed before the Big Bang? It's a question that seems simple, but it touches on the deepest mysteries of existence, time, and reality itself. For most of human history, the question would have seemed meaningless or unanswerable, relegated to the realm of philosophy and theology. But today, armed with powerful telescopes, sophisticated mathematics, and groundbreaking theories, scientists are beginning to explore this ultimate frontier. The answers they're finding are as strange and surprising as anything in science fiction. Some theories suggest the Big Bang wasn't the beginning at all, but a transition from a previous state. Others propose that time itself began with the Big Bang, making the question of before fundamentally meaningless. Still others suggest we might be living in one of countless universes in an eternal multiverse, where Big Bangs happen constantly throughout an infinite expanse. The implications are staggering. If there was something before the Big Bang, what was it? Was it another universe, a quantum foam of possibilities, or something entirely beyond our comprehension? Did the laws of physics as we know them apply, or was it governed by completely different rules? And perhaps most puzzling of all, if time itself began with the Big Bang, what does it even mean to ask what came before? These questions challenge our most basic assumptions about causality, existence, and the nature of reality. Before we embark on this journey to the very edge of knowledge and beyond, drop it in the comments below where in the world you're watching from and what time it is there. Now, settle in as we explore the theories, the evidence, and the profound implications of what might have existed before the universe as we know it began. The nature of the Big Bang. To understand what might have existed before the Big Bang, we first need to understand what the Big Bang actually was. Contrary to popular imagination, the Big Bang was not an explosion in space. It was an expansion of space itself. About 13.8 billion years ago, the universe existed in an incredibly hot, dense state, with all matter, energy, space, and time compressed into an infinitesimally small point. Then, space began expanding rapidly, carrying matter and energy along with it. As the universe expanded, it cooled, allowing particles to form, then atoms, then stars and galaxies. The evidence for the Big Bang is overwhelming. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, now known as Hubble's law, indicates that the universe is expanding. If we run the expansion backward in time, everything converges to a single point in the past. This was the moment of the Big Bang. Further evidence came in 1965 with the discovery of the cosmic microwave background, or CMB, a faint glow of radiation that fills the entire sky. This radiation is the cooled remnant of the intense heat from the early universe, released when the universe became transparent about 380,000 years after the Big Bang. Additional support comes from the observed abundances of light elements like hydrogen, helium, and lithium, which match the predictions of Big Bang nucleosynthesis, the process by which these elements were forged in the first few minutes after the Big Bang. The large-scale structure of the universe, with galaxies clustered in vast filaments and sheets, also matches predictions from models of how structure grew from tiny fluctuations in the early universe. All of this evidence points to a universe that was once much smaller, hotter, and denser, and that has been expanding and cooling for billions of years. However, the Big Bang theory, as successful as it is, has some puzzling features. One is the horizon problem. Different regions of the observable universe, now separated by vast distances, have nearly identical temperatures as measured in the cosmic microwave background. Yet, according to the standard Big Bang model, these regions were never in causal contact, never close enough for light to travel between them and equilibrate their temperatures. How, then, did they come to have the same temperature? Another puzzle is the flatness problem. The universe today appears to be spatially flat, with a geometry very close to Euclidean. But in the early universe, even a tiny deviation from perfect flatness would have been amplified by expansion, leading to a dramatically curved universe today. The fact that we observe a flat universe suggests an extraordinary fine-tuning of initial conditions. There's also the monopole problem. Some theories of particle physics predict the existence of magnetic monopoles, particles with only one magnetic pole, which should have been produced in large numbers in the early universe. Yet we have never observed a single magnetic monopole. Where did they all go? These problems led cosmologists to propose a modification to the Big Bang theory called cosmic inflation. According to this idea, in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the power of 26 inches, less than a trillionth of a second. Inflation solves the horizon problem by proposing that all the regions we see were once in close contact before being stretched apart by inflation. It solves the flatness problem by stretching any initial curvature to such large scales that the observable universe appears flat, and it dilutes magnetic monopoles to such low densities that we would never expect to find one. Inflation has become a cornerstone of modern cosmology, with strong observational support from the patterns of fluctuations in the cosmic microwave background. But inflation also raises a new question. What caused inflation? What set it in motion? And more importantly, what existed before inflation began? If inflation was the beginning of our universe's expansion, what was there before inflation? This is where the question of what existed before the Big Bang becomes concrete and scientifically tractable. The problem of time. One of the most profound challenges in asking what existed before the Big Bang is understanding the nature of time itself. In our everyday experience, time flows from past to future in a clear, unidirectional manner. We remember the past, but not the future, and causes precede their effects. This arrow of time seems fundamental to reality. But in physics, time is more subtle and complex than our intuition suggests. In Isaac Newton's mechanics, time is absolute, flowing uniformly regardless of what happens in the universe. Time is the backdrop against which events occur, a fixed stage on which the cosmic drama unfolds. In this view, it makes perfect sense to ask what existed before any given moment, including the Big Bang. Time stretches infinitely into the past and future, and the Big Bang would simply be an event that occurred at some point along this infinite timeline. But Einstein's theory of general relativity changed everything. In general relativity, time is not separate from space. They are woven together into a four-dimensional fabric called space-time. Matter and energy curve space-time, and this curvature is what we experience as gravity. Crucially, the structure of space-time itself is dynamic, affected by the distribution of matter and energy. In the context of the Big Bang, this means that time itself came into existence along with space and matter. The Big Bang is not an event that occurred in pre-existing time, it is the origin of time itself. If time began with the Big Bang, then the question of what existed before becomes problematic. The word before implies a temporal relationship, a moment in time that precedes another moment. But if time itself began with the Big Bang, there is no before. Asking what came before the Big Bang is like asking what is north of the North Pole. The question is based on a category error, applying a concept, temporal precedence, in a context where it does not apply. This perspective, articulated by physicists like Stephen Hawking, suggests that the Big Bang is not just the beginning of the universe, but the beginning of time itself, and therefore there is no before to speak about. However, this conclusion depends on taking general relativity as the final word on the nature of time. But general relativity, as powerful as it is not a complete theory. It breaks down at the extreme conditions of the Big Bang, where densities and temperatures become infinite, a situation known as a singularity. At a singularity, the equations of general relativity produce nonsensical results, infinities that cannot be physically meaningful. This suggests that general relativity is not the full story, and that a more fundamental theory, one that incorporates quantum mechanics, is needed to describe what happens at the Big Bang. Quantum mechanics, the theory that describes the behavior of particles at the smallest scales, has its own strange relationship with time. In quantum mechanics, time is treated as a parameter, an external backdrop against which quantum states evolve, rather than a dynamic entity that can be affected by matter and energy. Reconciling this with general relativity, where time is part of the dynamic fabric of space-time, is one of the great challenges of theoretical physics. A complete theory of quantum gravity, which would unify quantum mechanics and general relativity, might reveal that time has a more complex structure than either theory alone suggests. Some approaches to quantum gravity suggest that time might be an emergent phenomenon arising from more fundamental, timeless quantum processes. In this view, time as we experience it is not fundamental, but is a large-scale approximation like temperature or pressure, which emerge from the average behavior of countless microscopic particles. If time is emergent, then at the level of the Big Bang, where the universe is quantum and space-time breaks down, the concept of time might not apply in the usual way. There might be a timeless quantum state from which time, space, and the universe, as we know it, emerged. This opens the door to asking what this timeless state was like and whether it can be considered a kind of before, even if not in the conventional temporal sense. The quantum origin hypothesis. One of the most intriguing ideas about what existed before the Big Bang is that the universe emerged from a quantum fluctuation, a spontaneous event in the quantum realm that required no prior cause or conditions. This idea, sometimes called the quantum origin hypothesis or creation from nothing, is based on the strange and counterintuitive properties of quantum mechanics. In quantum mechanics, particles can spontaneously appear and disappear from the vacuum, the lowest energy state of a quantum field. These virtual particles, as they are called, exist for only a fleeting moment before annihilating back into the vacuum. Their existence is not a violation of energy conservation because of Heisenberg's uncertainty principle, which allows for temporary violations of energy conservation over very short timescales. The vacuum is not truly empty, but is a seething foam of quantum activity, with particles constantly popping in and out of existence. Could the entire universe have originated from such a quantum fluctuation? Physicist Edward Tryon proposed this idea in 1973, suggesting that the universe is a quantum fluctuation of the vacuum that happened to grow to macroscopic size rather than disappearing immediately. The idea sounds radical, but it is based on solid quantum mechanics. If the total energy of the universe is zero, which is possible if the positive energy of matter is exactly balanced by the negative gravitational potential energy, then the universe could emerge from the vacuum without violating energy conservation. In this view, the universe is the ultimate free lunch, arising from nothing and costing nothing. Physicist Alan Guth, who developed the theory of cosmic inflation, extended this idea by showing how a quantum fluctuation could lead to inflation. If a tiny region of space, far smaller than an atom, happened to be in a high-energy quantum state called a false vacuum, it could undergo exponential inflation, expanding to cosmic size in a fraction of a second. During inflation, the energy of the false vacuum is converted into matter and radiation, filling the universe with the particles and fields we observe today. The quantum fluctuations during inflation also seed the density variations that eventually grow into galaxies and large-scale structure. In this scenario, the Big Bang was not a singular event, but the transition from inflation to the hot, dense state we call the early universe. But where did the initial quantum fluctuation come from? If the universe emerged from a quantum vacuum, what was the nature of that vacuum? In some versions of the theory, the vacuum is a timeless, spaceless quantum state, a kind of nothing that nonetheless has the structure and laws of quantum mechanics. This nothing is not the absolute nothingness of philosophy, where literally nothing exists. It is a quantum nothing, a state governed by the laws of quantum field theory, where fields exist but have their minimum energy values. From this perspective, the laws of physics, or at least the principles of quantum mechanics, existed before the Big Bang, providing the framework from which the universe could emerge. Physicist Lawrence Krauss popularized this idea in his book, A Universe from Nothing, arguing that modern physics shows how the universe could have arisen from a quantum vacuum without any need for a creator or initial conditions. However, the idea is controversial. Critics, including philosophers and some physicists, argue that the quantum vacuum is not truly nothing because it already presupposes the existence of space, time, quantum fields, and physical laws. If these things existed before the Big Bang, then they themselves require explanation. The question simply shifts from why is there a universe to why are there laws of quantum mechanics and a quantum vacuum capable of producing universes. Despite these philosophical objections, the quantum origin hypothesis is scientifically fruitful because it makes predictions that can, in principle, be tested. For example, if the universe arose from a quantum fluctuation, there might be observable consequences in the patterns of the cosmic microwave background or in the distribution of matter on large scales. Some versions predict specific signatures of quantum effects that could be detected by future experiments. While we cannot observe the quantum origin directly, we can look for its fingerprints in the universe we see today, the cyclic universe. Another compelling answer to the question of what existed before the Big Bang is that there was a previous universe. According to cyclic or oscillating universe models, the Big Bang was not the beginning of everything, but just one phase in an eternal cycle of expansion and contraction. In this view, the universe undergoes repeated cycles, each beginning with a Big Bang, expanding for billions of years, then contracting back to a big crunch, which then bounces into a new Big Bang. The cycle repeats indefinitely, with no ultimate beginning or end. The idea of a cyclic universe has ancient roots. Many Eastern philosophies and religious traditions, including Hinduism and Buddhism, describe time as cyclical, with the cosmos undergoing endless cycles of creation and destruction. In the West, the pre-Socratic philosopher Empedocles proposed a cyclical cosmos, and later thinkers like Nietzsche contemplated eternal recurrence. But it was only in the 20th century, with the development of general relativity, that cyclic cosmologies could be formulated as scientific theories. In the 1,920 seconds and 1,930 seconds, some cosmologists proposed that if the universe contained enough matter, its expansion would eventually slow, stop, and reverse, leading to a contraction phase ending in a big crunch. However, it was unclear whether a bounce could occur at the big crunch to start a new cycle, or whether the universe would end in a singularity, a point of infinite density where the laws of physics break down. Most models suggested that a singularity was inevitable, which would mean the end of time and the impossibility of a new cycle. The discovery of dark energy in 1998 and the observation that the universe's expansion is accelerating rather than decelerating seemed to rule out cyclic models altogether. If the expansion continues to accelerate, the universe will expand forever, never recollapsing. However, in the early 2000s, physicists Paul Steinhardt and Neil Turok proposed a new version of the cyclic universe, inspired by ideas from string theory and extra dimensions. Their ekpyrotic model does not involve a traditional big crunch and bounce. Instead, it envisions our universe as a three-dimensional brain, a membrane, embedded in a higher dimensional space. The Big Bang occurs when our brain collides with another brain, releasing energy that we perceive as the hot, dense state of the early universe. In the ekpyrotic model, the brains exist in a higher dimensional bulk space, separated by a gap. Over time, the brains are attracted to each other by forces in the bulk, and eventually they collide, triggering a Big Bang. After the collision, the brains bounce apart, and the universe on each brain expands and evolves. Eventually, the brains slow, stop, and begin approaching each other again, leading to another collision and another Big Bang. This cycle can repeat indefinitely. The advantage of this model is that it avoids the singularities that plagued earlier cyclic models, because the brains never collapse to zero size. Instead, they collide at a finite separation and bounce, with the bounce mediated by quantum effects or higher dimensional physics. The ekpyrotic model makes specific predictions about the early universe that differ from standard inflation. For example, it predicts that the universe should be extremely flat and smooth, with density fluctuations that have particular statistical properties. Some of these predictions have been tested against observations of the cosmic microwave background, and so far the results are compatible with the model, though not uniquely supportive of it. The model also predicts that gravitational waves from the early universe should have very low amplitude, much lower than in standard inflation. Future gravitational wave detectors might be able to test this prediction. Another approach to cyclic cosmology is conformal cyclic cosmology, proposed by mathematical physicist Roger Penrose. Penrose suggests that the universe undergoes infinite cycles, but instead of contracting and bouncing, each cycle ends with the universe expanding to infinite size and becoming increasingly smooth and empty. In the far future, when all matter has decayed and black holes have evaporated, the universe reaches a state where there are no massive particles, only photons and other massless fields. Penrose argues that in this state, the concepts of time and scale lose their meaning, and the universe can be mathematically transformed into the initial conditions for a new Big Bang. Each cycle, which Penrose calls an eon, transitions smoothly into the next without a singular bounce. Penrose claims that there might be observational evidence for his model in the cosmic microwave background. He has searched for circular patterns that could be the signatures of collisions or other events from a previous eon, and he has reported finding some candidates, though the statistical significance and interpretation of these patterns are debated. Cyclic models offer an elegant solution to the question of what existed before the Big Bang: another universe, similar to our own, undergoing its own evolution. In this view, the Big Bang is not the beginning but a transition, and the question of the ultimate origin is avoided or deferred indefinitely. eternal inflation and the multiverse. One of the most revolutionary ideas in cosmology is eternal inflation. The proposal that inflation, once started, never completely ends. While inflation stops in some regions, allowing them to evolve into universes like ours, it continues in other regions, spawning new inflating regions indefinitely. This process creates a multiverse, an infinite collection of bubble universes, each with its own Big Bang, each potentially with different physical properties. Eternal inflation arises naturally from many models of inflation. Inflation is driven by a field called the inflaton, which has a potential energy that causes space to expand rapidly. As the inflaton field rolls down its potential, inflation ends and the energy is converted into particles and radiation, creating the hot Big Bang. However, quantum fluctuations in the inflaton field mean that in some regions, the field rolls uphill rather than downhill, causing inflation to continue locally. These regions expand exponentially, and within them, new regions stop inflating and form bubble universes, while others continue inflating. The process repeats indefinitely, with inflation generating an ever-growing fractal structure of inflating regions and bubble universes. In this scenario, our Big Bang was not the beginning of everything, but the beginning of our particular bubble universe. Before our Big Bang, there was an inflating region, and before that, perhaps another bubble universe, or another inflating region. The question of what existed before the Big Bang becomes, what existed in the broader, inflating multiverse at the time our bubble nucleated? The answer is that inflation was ongoing, perhaps for an infinite time into the past, producing countless other bubbles, each with its own history and properties. Eternal inflation has profound implications. It means that the universe is vastly larger and more diverse than the observable universe we see. Most of this multiverse is forever beyond our reach, causally disconnected by the rapid expansion. It also means that the physical constants and laws that we observe, such as the strength of gravity or the mass of the electron, might not be universal, but might vary from bubble to bubble. In some regions of the multiverse, the constants might be different, leading to entirely different physical phenomena. In some bubbles, stars and galaxies might not form, or atoms might not be stable, making life impossible. This raises the question of why we observe the particular constants and laws that we do. The anthropic principle offers one answer. We observe a universe with properties compatible with our existence, because we could not exist in a universe where those properties were different. In an infinite multiverse with varying constants, there will be some bubbles where conditions allow for the formation of galaxies, stars, planets, and life. We necessarily find ourselves in one of those rare bubbles, not because our bubble is special in any fundamental sense, but because only in such bubbles could observers like us arise to ask questions about the universe. Eternal inflation also addresses the question of the origin of inflation itself. If inflation has been going on eternally, then there is no need to explain how it started. It has simply always been happening, with no ultimate beginning. However, this idea faces challenges. Mathematician Arvin Bourdais and physicists Alan Guth and Alexander Vilenkin proved a theorem showing that even in eternal inflation, the universe must have had a beginning in the past if we follow space-time backward. The theorem applies to any universe that is, on average, expanding. It shows that there must be a boundary to the past, a point where space-time begins, even if inflation is eternal going forward. This result suggests that eternal inflation does not eliminate the need to explain the ultimate origin of the universe. It pushes the question back, but does not answer it. There must still be something, some initial condition or quantum state, from which eternal inflation began. What was that initial state? Was it a quantum fluctuation, a timeless quantum state, or something else entirely? The question remains open and is an active area of research. Quantum cosmology and the wave function of the universe. To truly understand what might have existed before the Big Bang, physicists need a theory that combines quantum mechanics and general relativity, a theory of quantum gravity. While such a theory does not yet exist in complete form, several approaches have been developed, and they offer tantalizing hints about the origin of the universe. One approach is quantum cosmology, which attempts to apply the principles of quantum mechanics to the universe as a whole. In quantum mechanics, the state of a system is described by a wave function, a mathematical object that encodes the probabilities of different outcomes when the system is measured. The wave function evolves according to the Schrödinger equation, which is deterministic, meaning that if you know the wave function at one time, you can calculate it at any other time. In quantum cosmology, the universe itself is treated as a quantum system, described by a wave function that encodes the probabilities of different possible geometries and matter configurations. One of the pioneers of quantum cosmology, John Wheeler, along with his student Bryce DeWitt, formulated the Wheeler-DeWitt equation, a quantum version of Einstein's equations for the universe. This equation does not include time explicitly. Instead, it describes the universe as a timeless quantum state, with time emerging as an effective concept when the universe becomes large and classical. Solving the Wheeler-DeWitt equation is extremely difficult, and it is not even clear what the solutions represent physically. Nonetheless, it provides a framework for thinking about the quantum nature of the universe. In the 1980 seconds, physicists James Hartle and Stephen Hawking proposed a specific solution to the Wheeler-DeWitt equation, known as the no-boundary proposal. They suggested that the wave function of the universe can be calculated by considering all possible geometries for space-time that have no boundary in the past. In this approach, the universe does not have a singular beginning. Instead, time becomes more and more like space as we go back toward the Big Bang, and the distinction between time and space blurs. Near the beginning, space-time is described by Euclidean geometry, where time is treated as if it were a spatial dimension. In this picture, asking what existed before the Big Bang is like asking what is south of the South Pole. The question does not make sense because there is no edge or boundary. Time simply curves back on itself. The no-boundary proposal avoids the need for initial conditions because the wave function is determined by the geometry of space-time itself. The universe, in this view, is self-contained, with no need for an external cause or prior state. Hawking often said that the no-boundary proposal showed how the universe could create itself from nothing, with the laws of physics, specifically quantum gravity, providing the mechanism. However, the proposal is controversial and faces several technical and conceptual challenges. The calculations involved require a procedure called Euclidean path integrals, which is not rigorously defined for gravity, and it is unclear whether the results are physically meaningful. An alternative approach, proposed by Alexander Vilenkin, is the tunneling proposal. Vilenkin suggests that the universe began as a quantum tunneling event from nothing, or more precisely, from a state with no classical space-time. In quantum mechanics, particles can tunnel through barriers that they classically could not surmount, appearing on the other side without having crossed the barrier in the usual sense. Vilenkin applies this idea to the universe itself, proposing that the universe tunneled from a state of zero size, a quantum nothing, into a small inflating bubble. This tunneling event is described by the wave function of the universe, and it does not require any prior time or space. Both the no-boundary and tunneling proposals aim to describe the origin of the universe without invoking anything before the Big Bang. They replace the question of what existed before with a description of how the universe could emerge from a quantum state. However, both proposals still assume the existence of quantum mechanics and the laws of physics. They do not explain why those laws exist or why they have the form they do. This leaves room for further questions about the ultimate origin of physical law itself, string theory, and the pre-Big Bang scenario. String theory, one of the leading candidates for a theory of quantum gravity, offers its own perspective on what might have existed before the Big Bang. In string theory, the fundamental constituents of reality are not point particles, but tiny, vibrating strings of energy. The different vibrational modes of these strings correspond to different particles, and the theory naturally incorporates gravity along with the other forces of nature. String theory also requires extra dimensions beyond the familiar 3 of space and 1 of time, typically 6 or 7 additional dimensions that are compactified or curled up at very small scales. One intriguing idea from string theory is the pre-Big Bang scenario, developed by Gabriele Veneziano and collaborators in the 1990 seconds. In this model, the Big Bang is not the beginning but a transition from a previous phase of the universe. Before the Big Bang, the universe was in a state dominated by different physics, governed by string theory rather than classical general relativity. This pre-Big Bang phase was cold, nearly empty, and gently contracting. As it contracted, quantum and stringy effects became important, and the universe underwent a bounce or transition, emerging into the hot, expanding phase we call the Big Bang. The pre-Big Bang scenario is motivated by a symmetry in string theory called duality, which relates large and small scales, strong and weak coupling, and other pairs of opposites. Using these dualities, Veneziano and his collaborators showed that the equations of string cosmology have solutions where the universe transitions from a contracting phase to an expanding phase. Before the transition, time runs backward compared to our usual notion, and the universe is in a state of low entropy and low temperature. The transition to the Big Bang involves a dramatic increase in entropy and temperature, creating the hot, dense state from which the universe as we know it emerged. This model provides a concrete answer to the question of what existed before the Big Bang, a pre-Big Bang universe with different properties governed by string theory. In this view, the Big Bang is a kind of phase transition or bounce, similar to the cyclic models, but motivated by the specific physics of string theory. The model makes predictions about the spectrum of gravitational waves and other observables that could, in principle, be tested. However, the pre-Big Bang scenario faces challenges, including the problem of explaining how the transition from contraction to expansion occurs without encountering singularities, and how to match the predictions to observations of the cosmic microwave background. String theory also connects to the idea of the multiverse through the concept of the landscape. As mentioned earlier, string theory allows for an enormous number of possible configurations of the extra dimensions, each leading to different values for the physical constants and different effective laws of physics. This landscape of possibilities might be realized in an eternal inflation scenario, where different regions of the multiverse correspond to different points in the landscape. In this view, before our Big Bang, there was an inflating multiverse exploring the landscape, and our universe is just one bubble in this vast structure. Another string-inspired idea is the ekpyrotic model, which we discussed in the context of cyclic cosmologies. The ekpyrotic model uses the brane world picture from string theory, where our universe is a brane in a higher dimensional space. The Big Bang occurs when branes collide, and before the collision, the branes existed in the bulk perhaps for an indefinite time. The model blurs the distinction between cyclic and multiverse scenarios, suggesting that both might be different perspectives on the same underlying reality. Loop, quantum gravity, and the Big Bounce. Loop quantum gravity is another approach to quantum gravity, distinct from string theory, that offers insights into what might have existed before the Big Bang. Unlike string theory, which introduces extra dimensions and new fundamental objects like strings and brains, loop quantum gravity attempts to quantize general relativity directly, treating space-time itself as fundamentally quantum. In loop quantum gravity, space is not continuous, but is made up of discrete, atom-like units, and time evolves in discrete steps. One of the key predictions of loop quantum gravity is that it resolves the singularities that appear in general relativity, including the singularity at the Big Bang. In classical general relativity, as we trace the universe backward in time, density and temperature increase without bound, leading to a singularity where the laws of physics break down. In loop quantum gravity, quantum effects become important at extremely high densities, preventing the collapse to a singularity. Instead of a Big Bang singularity, loop quantum gravity predicts a Big Bounce. In the Big Bounce scenario, the universe before the Big Bang was a previous universe that was contracting. As it contracted, it became hotter and denser, but before reaching infinite density, quantum gravitational effects halted the collapse and reversed it, causing the universe to bounce and begin expanding. This expanding phase is the Big Bang we observe. The bounce occurs because, in loop quantum gravity, there is a limit to how much matter and energy can be compressed into a given volume. When this limit is reached, a repulsive quantum force kicks in, preventing further collapse and driving the expansion. The Big Bounce model provides a clear answer to what existed before the Big Bang: a contracting universe that reached a minimum size and then rebounded. This previous universe might have been similar to ours, with galaxies, stars, and perhaps even life. Or it might have been radically different, depending on the conditions at the bounce. The model also raises the possibility of an infinite series of bounces, with each cycle potentially lasting billions or trillions of years. In this view, the cosmos is eternal, with no ultimate beginning or end, just an endless sequence of expansions and contractions. Loop quantum cosmology, the application of loop quantum gravity to cosmology, has been developed in detail over the past 2 decades. Simulations show that the bounce is robust and occurs under a wide range of initial conditions. The model also makes predictions about the early universe that differ from standard inflation. For example, it predicts specific patterns in the cosmic microwave background and in the distribution of matter on large scales. These predictions are being tested against observations, and so far the results are promising, though not yet definitive. One appealing feature of the Big Bounce is that it avoids the problem of initial conditions. In a bouncing universe, the conditions at the Big Bang are determined by the state of the previous contracting phase, which in turn was determined by an even earlier phase, and so on. There is no need to fine-tune the initial conditions of the universe, because they are inherited from the infinite past. However, this also means that the model does not explain the ultimate origin of the universe. It simply replaces the question of what came before the Big Bang with the assertion that there is always something before, stretching infinitely into the past. The role of entropy and the arrow of time. Any discussion of what existed before the Big Bang must grapple with the problem of entropy and the arrow of time. Entropy is a measure of disorder or randomness, and the second law of thermodynamics states that entropy always increases in an isolated system. This law is intimately connected to the arrow of time, the fact that time flows from past to future and not the other way round. We remember the past but not the future, and causes precede their effects. All of this is tied to the increase of entropy. One of the great puzzles in cosmology is why the entropy of the universe was so low at the Big Bang. The early universe was extremely smooth and uniform, with matter and energy distributed almost evenly throughout space. This is a state of very low entropy compared to what the universe could have been. If the universe had started in a state of maximum entropy, it would be a chaotic, structureless mess, and no complexity or life could ever arise. The fact that the universe started with low entropy is what allows for the rich variety of structures, from galaxies to planets to living organisms, that we see today. But why did the universe start with low entropy? In standard cosmology, this is simply taken as an initial condition, a boundary condition, imposed on the universe at the Big Bang. But this seems unsatisfying because it requires a very special, highly unlikely starting state. If the universe emerged from some prior state or process, that prior state should have higher entropy, not lower, in accordance with the second law. This creates a puzzle. How can a low entropy Big Bang emerge from a higher entropy prior state? One proposed solution is that the universe before the Big Bang was in a state of even lower entropy, and the Big Bang represents an increase in entropy from that prior state. This idea is explored in some cyclic models, where each cycle begins with low entropy and ends with high entropy, but the transition to the next cycle involves a decrease in entropy. However, decreasing entropy seems to violate the second law of thermodynamics, so some mechanism is needed to reset entropy at the bounce or transition. Loop quantum gravity might provide such a mechanism if the quantum effects at the bounce shuffle or rearrange the degrees of freedom in a way that effectively resets entropy. Another approach, proposed by physicist Roger Penrose in his conformal cyclic cosmology, suggests that entropy does not reset but continues to increase through each cycle. Penrose argues that in the far future of our current cycle, when all matter has decayed and the universe is filled only with photons, the concept of entropy becomes ill-defined because there are no massive particles to define a reference frame. In this state, the universe can be mathematically transformed into the initial conditions for a new cycle, with the transformation effectively redefining what we mean by low entropy. This is a subtle and controversial idea, and it remains to be seen whether it can be made rigorous. The problem of entropy also connects to the question of whether the multiverse can explain the low entropy Big Bang. In an eternal inflation scenario, different bubbles might have different entropy levels, and we naturally find ourselves in a bubble where entropy was low enough to allow for structure formation and life. This anthropic explanation is consistent with the second law, but does not explain why the multiverse as a whole exists, or why it has the properties that allow for low entropy bubbles to form. The arrow of time itself might also be emergent, rather than fundamental. Some theories propose that time is a large-scale approximation, arising from the statistical behavior of countless microscopic degrees of freedom. In the early universe, or in any quantum gravitational regime, the usual notions of time and causality might break down, and the arrow of time might not be well defined. If so, then asking what came before the Big Bang might not make sense in the usual temporal way, but it might make sense in some other, more abstract sense, related to the underlying quantum structure of reality, philosophical and theological implications. The question of what existed before the Big Bang is not just a scientific question. It touches on deep philosophical and theological issues that have been debated for millennia. The nature of existence, the origin of the universe, the relationship between time and eternity, and the question of whether there is a creator or ultimate cause are all intertwined with the scientific exploration of the Big Bang and what might have preceded it. In classical theology, particularly in the Judeo-Christian tradition, God is often described as the creator of the universe, existing outside of time and bringing the universe into being from nothing. The Big Bang, as a moment of origin, fits naturally into this framework, with the Big Bang being the moment of creation. However, the scientific theories we have discussed offer alternative accounts of the origin of the universe that do not require a creator, or at least not in the traditional sense. If the universe emerged from a quantum fluctuation, or from a prior contracting phase, or from an eternal multiverse, then the role of a creator becomes less clear. Some theologians and philosophers have argued that scientific accounts of the origin of the universe are compatible with belief in God, but they require a more sophisticated understanding of what it means to be a creator. Instead of thinking of God as a being who existed before the universe and caused it to come into being at a specific moment, one might think of God as the ground of all being, the reason why there are laws of physics, why there is something rather than nothing, and why the universe has the capacity to bring forth life and consciousness. In this view, scientific discoveries about the Big Bang and what preceded it do not diminish the role of God, but deepen our understanding of how creation works. Others argue that if the universe can arise from purely physical processes, without any need for supernatural intervention, then the hypothesis of God becomes unnecessary. The burden of proof shifts to those who believe in a creator to explain what role God plays if the universe can explain itself through natural laws. This debate between naturalism and theism has been reinvigorated by modern cosmology and shows no sign of being resolved anytime soon. Philosophically, the question of what existed before the Big Bang raises issues about causality and explanation. In philosophy, the principle of sufficient reason holds that everything that exists must have a reason or cause for its existence. If the universe had a beginning, what caused it to begin? If there was something before the Big Bang, what caused that prior state? And if we trace causes back infinitely, do we ever arrive at a final explanation, or does the chain of causation extend without end? Some philosophers, like Gottfried Leibniz, argued that there must be a necessary being, something that exists by its own nature and does not require a cause to ground the chain of contingent beings. Others, like David Hume, questioned whether the principle of sufficient reason is valid at all, especially when applied to the universe as a whole. The possibility of a multiverse raises additional philosophical questions. If there are infinitely many universes, each with different properties, does that diminish the significance of our universe? Some argue that it does, reducing our universe to just one random fluctuation among countless others. Others argue that it enhances the significance of our universe because it shows that the conditions for life and consciousness are extraordinarily rare and special. The anthropic principle, which explains our observations by noting that we can only exist in a universe compatible with our existence, is sometimes criticized as tautological or unscientific, but it may be the best explanation we have if the multiverse is real. The question of time and eternity also has deep philosophical and theological dimensions. If time began with the Big Bang, then the universe has a finite age, and the past is bounded. But if time is eternal, or if the universe undergoes infinite cycles, then there is no ultimate beginning, and the past stretches infinitely backward. The idea of an eternal universe has been appealing to some philosophers and scientists because it avoids the problem of explaining an ultimate origin. But it also raises the question of why anything exists at all, a question that an eternal universe does not answer any more than a finite one does. Observational evidence and future tests. While much of the discussion about what existed before the Big Bang is theoretical and speculative, There are observational programs and future experiments that might provide evidence for or against various scenarios. The cosmic microwave background remains one of the most important sources of information about the early universe, and future observations with higher precision might reveal subtle signatures of pre-Big Bang physics. One key observable is the spectrum of primordial gravitational waves. Gravitational waves are ripples in spacetime produced by accelerating masses or by quantum fluctuations in the early universe. Inflation predicts a specific spectrum of gravitational waves, characterized by their amplitude and frequency dependence. Different models of what preceded the Big Bang, such as the ekpyrotic model or loop quantum cosmology, predict different spectra. By measuring the gravitational wave background, either through its imprint on the cosmic microwave background or through direct detection by gravitational wave observatories, astronomers can test these models. The polarization patterns in the cosmic microwave background, specifically the B-mode polarization produced by gravitational waves, are a particularly promising target. Experiments like BICEP, Planck, and future missions such as Lightbird and CMBS-4 are searching for these patterns. The detection of primordial B-mode polarization would provide strong evidence for inflation and would constrain the energy scale at which inflation occurred. The absence of detectable B-modes would favor models like the ekpyrotic scenario, which predict very low amplitudes for primordial gravitational waves. Another observable is the statistical properties of the density fluctuations in the early universe. These fluctuations, which are imprinted in the cosmic microwave background and in the large-scale structure of the universe, have specific statistical properties, such as their amplitude, scale dependence, and non-Gaussianity. Different models of the pre-Big Bang phase predict different properties. For example, the no-boundary proposal predicts a nearly scale-invariant spectrum with very small non-Gaussianity, while the ekpyrotic model predicts a slightly different scale dependence and potentially larger non-Gaussianity. By measuring these properties with high precision, cosmologists can distinguish between models. Observations of the large-scale structure of the universe, including the distribution of galaxies and the clustering of dark matter, also provide tests. Upcoming surveys, like the Vera C, Rubin Observatory, the Euclid mission, and the Nancy Grace Roman Space Telescope, will map the distribution of galaxies and measure gravitational lensing with unprecedented accuracy. These observations will constrain the history of cosmic expansion and the growth of structure, providing indirect information about the early universe and potentially about any pre-Big Bang phase. Gravitational wave astronomy is still in its infancy, but it has already opened a new window on the universe. The detection of merging black holes and neutron stars by LIGO and Virgo has confirmed the existence of gravitational waves and provided new ways to study compact objects and test general relativity. Future detectors, including the space-based LISA mission and next-generation ground-based detectors, will be sensitive to lower-frequency gravitational waves and might detect signals from the early universe, including from phase transitions, cosmic strings, or other exotic phenomena associated with the Big Bang or a pre-Big Bang phase. Particle physics experiments, such as those at the Large Hadron Collider and future colliders, also have a role to play. The physics of the early universe is intimately connected to particle physics because the conditions shortly after the Big Bang involved energies far higher than anything we can produce in laboratories. Discoveries of new particles or forces, or measurements of the properties of known particles like the Higgs boson, can provide insights into the fundamental laws that govern the early universe. Some theories of what preceded the Big Bang, such as those involving extra dimensions or new fields, make predictions about particle physics that could be tested experimentally, limits of knowledge, and the nature of science. As we push toward the ultimate question of what existed before the Big Bang, we inevitably confront the limits of human knowledge. There are fundamental constraints, both practical and theoretical, on what we can know about the earliest moments of the universe and whatever might have preceded them. Understanding these limits is important for appreciating both the power and the boundaries of science. One fundamental limit is observational. We can only observe the universe back to the surface of last scattering, the moment when the cosmic microwave background was emitted. Before that, the universe was opaque and light could not travel freely. In principle, we could probe earlier times using neutrinos or gravitational waves, which can pass through the opaque plasma. But detecting primordial neutrinos or gravitational waves from the very early universe is extraordinarily challenging. Even if we could detect them, there is a limit to how far back we can see. At the Planck time, about 10 to the minus 43 seconds after the Big Bang, quantum gravitational effects dominate, and the classical notions of space and time break down. Beyond this point, our current theories do not apply, and we enter the realm of speculation. There is also a theoretical limit related to the breakdown of our physical theories. General relativity predicts singularities, points where physical quantities become infinite and the theory fails. Quantum mechanics provides some hints about how to avoid singularities, but a complete theory of quantum gravity is still lacking. Without such a theory, we cannot make reliable predictions about what happens at the Big Bang or before it. The theories we have discussed, from string theory to loop quantum gravity to quantum cosmology, are all incomplete and speculative to varying degrees. They offer frameworks and possibilities, but none has been definitively confirmed. Another limit is epistemological, related to the nature of scientific knowledge. Science proceeds by making observations, forming hypotheses, testing predictions, and revising theories in light of new evidence. But if certain aspects of the universe, such as regions beyond our cosmic horizon or events before the Big Bang, are in principle unobservable, can we make scientific statements about them? Some philosophers of science argue that unobservable entities should not be part of science, while others argue that theoretical inference is a legitimate part of science as long as the theories are coherent, mathematically precise, and connected to observable consequences in some way. The multiverse is a case in point. If there are other universes that are causally disconnected from ours, we can never observe them directly. Does this mean the multiverse is not a scientific concept? Advocates argue that the multiverse is a prediction of well-established theories like inflation and string theory, and that we can test these theories through their observable consequences in our universe. If inflation is confirmed by observations, and if inflation generically leads to eternal inflation and a multiverse, then the multiverse is a scientific consequence, even if the other universes themselves are not observable. Critics counter that, without direct observational access, the multiverse remains speculative, and that postulating unobservable entities risks turning science into metaphysics. There is also the question of whether mathematics alone can determine physical reality. The mathematical structures of quantum mechanics, general relativity, and other theories are extraordinarily successful at describing the universe. But why should mathematics correspond to reality? Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics, and it remains a deep philosophical puzzle. Some, like Max Tegmark, argue that physical reality is mathematical structure, and that all mathematically consistent structures exist in some sense. If this is true, then the question of what existed before the Big Bang might be answered by exploring the mathematical possibilities, even if we cannot observe them directly. Despite these limits, science has repeatedly shown that it can make progress on questions that once seemed unanswerable: the age of the universe, the origin of the elements, the existence of other galaxies, the expansion of space. All of these were once mysteries beyond the reach of science. Through ingenuity, careful observation, and theoretical insight, scientists have found answers. The question of what existed before the Big Bang may be at the current limits of knowledge, but it is not necessarily beyond those limits forever. The meaning of cosmic origins. As we conclude this exploration of what might have existed before the Big Bang, it is worth reflecting on what the quest to answer this question means for humanity. Why do we care about the origin of the universe? What difference does it make to our lives whether the Big Bang was the beginning or a transition, whether time is finite or infinite, whether we live in a single universe or a multiverse? On one level, the question is driven by pure curiosity, a desire to understand the world around us and our place in it. Humans have always asked questions about origins. Where do we come from? How did the world begin? What is the nature of existence? These questions are found in the myths and cosmologies of every culture, from the creation stories of ancient religions to the philosophical inquiries of Greek thinkers to the scientific investigations of modern cosmologists. The drive to know is part of what makes us human, and the question of what existed before the Big Bang is simply the latest expression of this timeless quest. On another level, the question has practical implications for science and technology. Understanding the early universe and the fundamental laws of physics has led to countless technological innovations. From GPS satellites that rely on general relativity to medical imaging devices that use principles from quantum mechanics, the pursuit of knowledge about the cosmos has driven the development of new instruments, new mathematical techniques, and new ways of thinking that have applications far beyond cosmology. Investments in fundamental science, including cosmology, pay dividends in unexpected ways, enriching our civilization and improving our lives. But perhaps the deepest significance of the question lies in how it shapes our worldview and our sense of meaning. If the universe had a definite beginning, a moment of creation from nothing, it suggests a certain narrative arc to cosmic history, with a starting point and perhaps an ending point as well. If the universe is eternal or part of an infinite multiverse, it suggests a very different picture, one of endless cycles or infinite diversity with no ultimate beginning or end. These different visions of the cosmos can influence how we think about our own lives, our place in the universe, and the significance of our actions. For some, the idea that the universe might have emerged from nothing, or from a quantum fluctuation, or from purely physical processes, is empowering and liberating. It shows that the cosmos is comprehensible, governed by laws that we can discover and understand, without the need for supernatural explanations. It affirms the power of human reason and the potential for science to answer even the most profound questions. For others, the same ideas might seem cold or empty, reducing the richness of existence to mere physical processes and leaving no room for meaning or purpose beyond what we create ourselves. For those with religious or spiritual perspectives, the scientific theories about the Big Bang and what preceded it can be integrated into a larger framework of meaning. The fact that the universe is vast, ancient, and governed by elegant laws can be seen as evidence of a creator's design or as a reflection of a deeper order that underlies reality. The question of why there is something rather than nothing, why the laws of physics are what they are, and why the universe is structured in a way that allows for life and consciousness, are questions that science can inform but may not fully answer. they leave room for philosophical and theological reflection. Ultimately, the significance of the question, what existed before the Big Bang, is that it pushes us to the very edge of human understanding. It challenges us to think deeply about time, causality, existence, and the nature of reality itself. It reminds us that despite all our progress, there are still profound mysteries, and that the universe is far stranger and more wonderful than our ancestors could have imagined. Whether we ever find a definitive answer or not, the journey of exploration is valuable, expanding our knowledge, deepening our appreciation for the cosmos, and inspiring us to keep asking questions and seeking truth. The current state of research. Where does the scientific community stand today on the question of what existed before the Big Bang? The honest answer is that we do not know. There are multiple competing theories, each with its own strengths and weaknesses, and each offering a different picture of the pre-Big Bang state. No single theory has been definitively confirmed, and it is possible that elements from several theories will eventually be combined into a more complete understanding. Cosmic inflation remains the leading paradigm for describing the very early universe, and it has strong observational support from the cosmic microwave background. However, inflation does not explain what caused it to begin or what existed before it started. Eternal inflation and the multiverse are natural extensions of inflation, but they raise new questions about the ultimate origin of the inflating state and about the testability of the multiverse hypothesis. Cyclic cosmologies, including the ekpyrotic model and conformal cyclic cosmology, offer intriguing alternatives that avoid the problem of an absolute beginning, but they face challenges in explaining the details of the transition from one cycle to the next and in matching all the observational data. Loop quantum cosmology and the Big Bounce provide a mechanism for resolving the Big Bang singularity, but the theory of loop quantum gravity itself is still under development and has not been fully tested. Quantum cosmology, including the no-boundary proposal and the tunneling proposal, attempts to describe the origin of the universe using quantum mechanics, but the mathematical foundations are not fully rigorous, and the physical interpretation is unclear. String theory offers a rich framework for thinking about the early universe and pre-Big Bang scenarios, but the theory is not yet complete, and its predictions are difficult to test directly. The scientific community is actively working on all these fronts, developing the theories, refining the mathematics, and designing new observations and experiments to test the predictions. There is a healthy debate, with different groups advocating for different approaches and critiquing each other's ideas. This is how science progresses, through the competition and collaboration of ideas, with empirical evidence ultimately serving as the arbiter. In the coming decades, new data from telescopes, gravitational wave detectors, particle accelerators, and other instruments will provide crucial tests of these theories. The cosmic microwave background will be mapped with even greater precision, searching for subtle signatures of inflation, bounces, or other exotic phenomena. Gravitational wave astronomy will mature, potentially detecting primordial signals from the early universe. Advances in theoretical physics, including progress toward a complete theory of quantum gravity, will clarify the conceptual foundations and make more precise predictions. It is possible that within our lifetimes, or within the lifetimes of the next generation of scientists, we will have a much clearer answer to the question of what existed before the Big Bang. We might confirm that the Big Bang was truly the beginning, with time and space emerging from a quantum state. Or we might discover evidence for a pre-Big Bang phase, a previous universe, or an eternal multiverse. Or we might find that the question itself needs to be reformulated in light of new insights into the nature of time and causality. Whatever the outcome, the quest to answer this question is one of the great scientific adventures of our time. It represents the human spirit at its best, curious, imaginative, rigorous, and unafraid to tackle the deepest mysteries of existence. The universe is calling us to explore its origins, and with the tools of modern science, we are answering that call. Thank you for joining me on this journey to the very edge of existence and perhaps beyond. If you enjoyed this exploration, make sure to like this video, subscribe to the channel, and hit the notification bell so you never miss future content. Drop a comment below with your thoughts. What do you think existed before the Big Bang? Do you think it's a question that science can ever truly answer? And if you want to support the channel and help us create more deep dives into the cosmos, consider becoming a patron or checking out our merchandise. Until next time, keep looking up, keep asking questions, and never stop wondering about the profound mysteries that lie at the heart of reality. The cosmos is vast, ancient, and full of secrets waiting to be discovered, the landscape of theoretical possibilities. To fully appreciate the range of answers to what existed before the Big Bang, we need to map out the landscape of theoretical possibilities that physicists and cosmologists have explored. Each possibility rests on different assumptions about the nature of space, time, matter, and the laws of physics. By examining these possibilities systematically, we can better understand what kinds of answers are even conceivable and what kinds of evidence might distinguish between them. The first major category is that nothing existed before the Big Bang, because before is a meaningless concept. In this view, articulated most famously by Stephen Hawking and others, time itself began at the Big Bang, and asking what came before is like asking what is north of the North Pole. This position takes seriously the implications of general relativity, which treats time as part of the dynamic structure of space-time rather than as an external parameter. If space-time had a boundary in the past at the Big Bang, then there simply is no time coordinate that extends before that boundary. However, even within this category, there are important distinctions. One version, based on classical general relativity, says that the Big Bang was a true singularity, a point where physical quantities become infinite and the laws of physics break down. At a singularity, the equations of general relativity cannot be extended further into the past, so the Big Bang represents an absolute boundary. Another version, informed by quantum mechanics and proposals like the no-boundary condition, suggests that the singularity is smoothed out by quantum effects. Near the Big Bang, space-time becomes quantum, and time gradually transitions into something more like a spatial dimension, creating a smooth, self-contained geometry with no edge or boundary. The second major category is that something did exist before the Big Bang, and the Big Bang was not the ultimate beginning, but a transition or transformation. This category includes a variety of scenarios, each proposing different states or processes that preceded our Big Bang. One subcategory is cyclic or bouncing cosmologies, where the universe undergoes repeated cycles of expansion and contraction. In these models, before our Big Bang, there was a previous contracting universe that reached a minimum size and then bounced into the expanding phase we observe. The bounce might be driven by quantum effects, as in loop quantum cosmology, or by higher dimensional physics, as in the ekpyrotic model. Another subcategory within this second category is the idea of a pre-Big Bang phase with different physics. This includes scenarios from string theory, where the universe before the Big Bang was in a cold, nearly empty state governed by stringy dynamics, which then underwent a transition to the hot, dense Big Bang state. It also includes models where the universe emerged from a higher dimensional space or from a different branch of the wave function in quantum cosmology. In these scenarios, the physics before the Big Bang might be radically different from the physics we observe today, with different effective dimensionality, different symmetries, or different fundamental fields. A third major category is the multiverse scenarios, where our Big Bang is just one event in a much larger, possibly eternal structure. In eternal inflation, inflation never completely ends but continues in some regions while stopping in others, creating a fractal structure of inflating space and bubble universes. Each bubble experiences its own Big Bang when inflation ends locally, but the broader inflating space has no beginning. It simply exists eternally. Before our Big Bang, in this view, there was inflating space and perhaps other bubbles that had already formed and evolved. Our universe is one of countless others, each with its own history. A fourth category, which overlaps with some of the others, is that the universe, or multiverse, exists as a timeless quantum state, and time itself is an emergent phenomenon that only makes sense in certain regions or under certain conditions. In this view, asking what existed before the Big Bang is not quite the right question, because the fundamental reality is timeless. The appearance of time and the sequence of events from Big Bang to the present is a large-scale, approximate description that emerges from an underlying timeless quantum state. This perspective is suggested by some approaches to quantum gravity and by the Wheeler-DeWitt equation, which describes the universe without reference to time. Each of these categories represents a fundamentally different worldview, with different implications for the nature of reality, causality, and existence. Distinguishing between them requires both theoretical work to flesh out the details and observational work to find signatures that can test the predictions. In some cases, the differences might be empirically testable. For example, different models predict different patterns in the cosmic microwave background or different spectra of gravitational waves. In other cases, the differences might be more philosophical or interpretive, with multiple theories fitting the same data but offering different ontological pictures of what really exists. The mathematics of creation, understanding what might have existed before the Big Bang, requires not just physical intuition, but also sophisticated mathematics. The equations that describe the early universe and the possible states that preceded it are among the most complex and abstract in all of physics. Yet these equations are not mere abstractions. They encode deep truths about the structure of reality and make predictions that can be tested against observations. Let us explore some of the key mathematical frameworks that physicists use to think about the Big Bang and what might have come before. General relativity, Einstein's theory of gravity, is the foundation of modern cosmology. The Einstein field equations relate the curvature of space-time to the distribution of matter and energy. In cosmology, these equations are simplified by assuming that the universe is homogeneous and isotropic on large scales, meaning it looks the same in all directions and at all locations. This assumption leads to the Friedmann equations, which describe how the scale factor of the universe, a measure of its size, evolves over time. The Friedmann equations show that if the universe contains matter and energy, it must either be expanding or contracting. They also predict that if we run the expansion backward in time, the scale factor goes to zero, corresponding to a singularity at the Big Bang. However, singularities in general relativity indicate a breakdown of the theory. At a singularity, physical quantities like density and temperature become infinite, and the equations cannot be solved. This is a sign that general relativity is incomplete, and that quantum effects, which general relativity does not include, must become important. To understand what happens at or before the Big Bang, we need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity. Several approaches to quantum gravity have been developed, each with its own mathematical structure. String theory is perhaps the most well-known. In string theory, the fundamental objects are not point particles, but one-dimensional strings that vibrate in different modes. The vibrations correspond to different particles, and the theory includes gravity as one of the vibrational modes, represented by the graviton. String theory requires extra spatial dimensions, typically 6 or 7 beyond the familiar 3, which are compactified or curled up at very small scales. The mathematics of string theory is extraordinarily rich, involving concepts from algebraic geometry, topology, and advanced calculus. String theory has led to insights about black holes, dualities, and the holographic principle, which suggests that the information in a volume of space can be encoded on its boundary. In the context of cosmology, string theory provides several frameworks for thinking about the Big Bang and what preceded it. One is the pre-Big Bang scenario, where the universe transitions from a cold, contracting phase to a hot, expanding phase, with the transition mediated by stringy effects. Another is the ekpyrotic model, where the Big Bang is caused by the collision of brane, higher dimensional objects in a bulk space. The mathematics of these models involves solving the equations of motion for branes and fields in higher dimensional spacetime, often using dualities to relate different descriptions of the same physics. Loop quantum gravity is another approach that takes a different starting point. Instead of replacing point particles with strings, loop quantum gravity quantizes spacetime itself. The theory represents spacetime as a network of quantum loops, called spin networks, which evolve over time. The mathematics involves techniques from quantum field theory and general relativity, but applied to the geometry of spacetime rather than to matter fields. In loop quantum gravity, space is fundamentally discrete, made up of finite quantized units, and this discreteness prevents the formation of singularities. The equations of loop quantum cosmology, applied to the universe as a whole, predict a big bounce rather than a big bang, with quantum effects halting the collapse and driving a re-expansion. Quantum cosmology attempts to describe the universe using the principles of quantum mechanics, treating the universe itself as a quantum system. The central object is the wave function of the universe, which encodes the probabilities for different configurations of space-time and matter. The wave function evolves according to the Wheeler-DeWitt equation, a quantum version of the Einstein field equations. Solving the Wheeler-DeWitt equation is extremely difficult, and it is not even clear what the solutions mean physically. The no-boundary proposal of Hartland-Hawking and the tunneling proposal of Vilenkin both attempt to specify the wave function of the universe using different boundary conditions or principles. The mathematics of these proposals involves path integrals, a technique from quantum mechanics where one sums over all possible histories or configurations, weighted by a phase factor, to compute probabilities. In quantum cosmology, the histories are different space-time geometries, and the path integral sums over all possible geometries that satisfy certain conditions. The no-boundary proposal uses Euclidean path integrals, where time is treated as an imaginary quantity, and the sum is over compact, four-dimensional geometries with no boundary. The result is a wave function that describes a universe that begins smoothly, without a singularity, with time emerging from a more spatial-like dimension. The mathematics underlying these theories is not just a tool for calculation, it reveals the deep structure of physical law. The equations are not arbitrary, but are constrained by symmetries, principles, and consistency conditions. For example, the Einstein field equations follow from the principle of general covariance, which says that the laws of physics should be the same in all coordinate systems. String theory is constrained by the requirement of quantum consistency, and by dualities that relate different string theories. Loop quantum gravity is built on the principles of background independence and diffeomorphism, invariance. These mathematical structures guide physicists in constructing theories and making predictions. Understanding the mathematics also reveals the limitations of our current knowledge. The Wheeler-DeWitt equation, for example, does not include a time parameter, suggesting that time is not fundamental. But what does it mean for the universe to exist without time? How do we interpret the wave function of the universe if there is no external observer to measure it? These are not just technical problems, but deep conceptual issues that challenge our understanding of quantum mechanics and reality itself. The mathematics provides a language for discussing these issues, but it does not always provide clear answers. The anthropic principle and fine-tuning. One of the most intriguing aspects of the question what existed before the Big Bang is the problem of fine-tuning and the role of the anthropic principle. Observations show that the fundamental constants of nature, such as the strength of gravity, the charge of the electron, and the mass of the Higgs boson, appear to be finely tuned to allow for the existence of stars, planets, and life. If any of these constants were even slightly different, the universe would be radically different, and life as we know it could not exist. This raises the question, why do the constants have the values they do? Is there some deep principle that determines them? Or are they just accidents? One answer, which connects to the question of what existed before the Big Bang, is the anthropic principle. In its weak form, the anthropic principle simply observes that the constants must be compatible with our existence, because otherwise we would not be here to observe them. This is a tautology, but a useful one. If there is only one universe with one set of constants, then the anthropic principle does not explain why those constants are what they are. It just notes that we could not exist in a universe with different constants, so we necessarily find ourselves in a universe where the constants allow for life. However, if there is a multiverse, with many different regions or bubble universes each having different constants, then the anthropic principle becomes a powerful explanation. In a multiverse, most regions will have constants that do not allow for the formation of atoms, stars, or galaxies, let alone life. But some tiny fraction of regions, by chance, will have constants in the narrow range that permit structure and complexity. We necessarily find ourselves in one of those rare regions, not because our region is special in any fundamental way, but because only in such regions could observers like us arise to ask questions about the universe. This is sometimes called anthropic selection. The multiverse scenarios we have discussed, such as eternal inflation and the string theory landscape, naturally give rise to a vast diversity of physical conditions. In eternal inflation, different bubble universes can have different values for the vacuum energy, the Higgs field, and other parameters, depending on how the inflaton field settled into its lowest energy state. In the string theory landscape, different compactifications of the extra dimensions lead to different effective laws of physics in 4 dimensions. With 10 to the power of 500 or more possible configurations, the landscape is so vast that almost any value for the constants can be realized somewhere. If this picture is correct, then the fine-tuning of our universe is not a mystery requiring a special explanation. It is simply a consequence of the fact that we could not exist in the vast majority of universes. So we observe one of the rare ones where conditions are right. The question of what existed before the Big Bang, in this context, is related to the question of what mechanism produced the multiverse and the diversity of physical constants. If eternal inflation or some other process generated countless universes before and alongside ours, then the anthropic principle explains our observations. However, the anthropic principle is controversial. Some physicists and philosophers argue that it is not a scientific explanation at all because it does not make testable predictions. If every possible outcome occurs somewhere in the multiverse, then the theory can explain anything and therefore explains nothing. Others argue that the anthropic principle is a legitimate form of reasoning. Similar to how we explain why Earth has the properties it does, it is one planet among many, and we happen to live on one that is habitable. The debate continues, and it touches on fundamental questions about what counts as a scientific explanation and what kinds of evidence are needed to support a theory. Fine-tuning also has theological implications. Some argue that the fine-tuning of the constants is evidence for intelligent design, for a creator who deliberately set the constants to allow for life. If the universe is unique, and if the constants could have had any values but happen to have the precise values needed for life, that seems to require an explanation, and a designer is one possible explanation. However, if the multiverse is real, then the fine-tuning is explained without recourse to design. The existence of the multiverse, thus, has implications for debates about God and the meaning of the universe, though it does not definitively resolve those debates. Interestingly, even in a multiverse, there are questions about fine-tuning. Why does the multiverse have the structure it does? Why are the laws of physics such that they allow for multiple universes with varying constants? Why is there quantum mechanics, or string theory, or whatever framework generates the multiverse? The anthropic principle can explain why we observe the particular constants we do, but it does not explain why there is something rather than nothing, or why the ultimate laws are what they are. These meta-level questions remain, and they push us back toward philosophical and theological considerations, experimental signatures, and ongoing research. While much of the discussion about what existed before the Big Bang is theoretical, there are concrete research programs aimed at finding observational signatures that could distinguish between different scenarios. The cosmic microwave background, gravitational waves, and large-scale structure all encode information about the early universe, and with sufficiently precise measurements, we might be able to detect fingerprints of a pre-Big Bang phase or a bounce or other exotic phenomena. One of the most important observables is the spectrum of primordial gravitational waves. Inflation predicts that quantum fluctuations during inflation generate gravitational waves, ripples in space-time, with a nearly scale-invariant spectrum. The amplitude of these gravitational waves depends on the energy scale of inflation, and detecting them would provide a direct measurement of that scale. Different pre-Big Bang scenarios predict different gravitational wave spectra. For example, the ekpyrotic model predicts a very low amplitude, much lower than in standard inflation, because the bounce mechanism suppresses gravitational wave production. Loop quantum cosmology predicts modifications to the spectrum at high frequencies, corresponding to the Planck scale, where quantum gravitational effects become important. Gravitational waves from the early universe can be detected in two ways. One is through their imprint on the cosmic microwave background. Gravitational waves produce a specific pattern of polarization in the CMB, called B-mode polarization, which can be distinguished from the more common E-mode polarization produced by density fluctuations. Several experiments, including BICEP, Planck, and upcoming missions like Lightbird and CMBS-4, are searching for primordial B-modes. So far, no definitive detection has been made, but the sensitivity of these experiments is improving, and within the next decade or two, we may either detect the signal or place stringent upper limits on the amplitude of primordial gravitational waves. Another way to detect gravitational waves is through direct observation using detectors like LIGO, Virgo, and the future space-based mission LISA. These detectors are sensitive to lower frequency gravitational waves, including potentially those from phase transitions, cosmic strings, or other sources in the very early universe. LISA, in particular, will be able to detect gravitational waves with frequencies too low for ground-based detectors, opening a new window on the early universe. If there were a phase transition associated with the Big Bang or a bounce, it might produce a stochastic background of gravitational waves that LISA could detect. The patterns of density fluctuations in the early universe, as measured in the CMB and in the large-scale structure, also provide tests of pre-Big Bang scenarios. Standard inflation predicts that these fluctuations should be nearly Gaussian, meaning their statistical properties follow a specific mathematical distribution, and nearly scale invariant, meaning they have similar amplitudes at all scales. Any deviation from Gaussianity or scale invariance would indicate new physics. Some pre-Big Bang models, such as the ekpyrotic scenario, predict specific non-Gaussian features that could be detected with sufficiently precise measurements. The Planck satellite has already measured the fluctuations to high precision, and upcoming surveys will push even further, searching for subtle anomalies that could point to exotic physics. Another observable is the spectrum of primordial elements produced by Big Bang nucleosynthesis. The abundances of hydrogen, helium, lithium, and other light elements depend on the conditions in the first few minutes after the Big Bang, including the density of ordinary matter, the expansion rate, and the presence of any additional particles or fields. If there were a pre-Big Bang phase or a bounce that affected these conditions, it might leave a signature in the element abundances. Current measurements of element abundances are consistent with standard Big Bang nucleosynthesis, but there are some puzzles, such as the lithium problem, where observations of old stars show less lithium than predicted. Resolving these puzzles might provide clues about the early universe. Observations of the large-scale structure of the universe, including the distribution of galaxies and the clustering of dark matter, also constrain models of the early universe. Upcoming surveys like Euclid, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope will map the distribution of galaxies and measure weak gravitational lensing with unprecedented accuracy. These observations will test the growth of structure over cosmic history and probe the nature of dark matter and dark energy. They will also provide indirect information about the initial conditions set by inflation or whatever process preceded the Big Bang. In addition to these observational programs, there is ongoing theoretical work to develop and refine the models of pre-Big Bang scenarios. String theorists are exploring the landscape of possible vacua and the dynamics of branes and extra dimensions. Loop quantum gravity researchers are improving the mathematical rigor of the theory and extending it to include matter and more realistic cosmologies. Quantum cosmologists are working to make sense of the wave function of the universe and to develop new proposals for the initial state. All of this work is interconnected, with ideas and techniques flowing between different approaches. There are also efforts to connect cosmology with particle physics. The conditions in the very early universe involved energies far higher than anything we can produce in particle accelerators, but the physics of the early universe is intimately related to the physics of fundamental particles and forces. Discoveries at the Large Hadron Collider, such as the properties of the Higgs boson or the possible detection of new particles, provide constraints on models of the early universe. Conversely, cosmological observations can provide insights into particle physics that are not accessible through laboratory experiments. This interplay between cosmology and particle physics is a rich and active area of research. The philosophical challenge of infinite regress. One of the deepest philosophical challenges raised by the question of what existed before the Big Bang is the problem of infinite regress. If we propose that there was something before the Big Bang, then we can ask what existed before that, and so on. Where does the chain of causation end, if it ends at all? This problem has occupied philosophers for millennia, and it remains unresolved even in the context of modern cosmology. In classical philosophy, the problem of infinite regress is often discussed in the context of the cosmological argument for the existence of God. The argument, formulated by thinkers like Thomas Aquinas and Leibniz, goes roughly as follows. Everything that exists has a cause or explanation for its existence. But if we trace the chain of causes backward, we cannot go on forever, because an infinite regress of causes is unsatisfying or incoherent. Therefore, there must be a first cause, something that is uncaused or that exists by its own nature, which is identified with God. This first cause is necessary, existing in all possible worlds, while everything else is contingent, existing only because it was caused by something else. The question of what existed before the Big Bang can be seen as a version of this problem. If the Big Bang was not the absolute beginning, if there was something before it, then what caused that prior state? And what caused the state before that? If we adopt a cyclic cosmology, with endless cycles of expansion and contraction, then we avoid the problem of a first cause, but we are left with an infinite regress of cycles stretching into the past. If we adopt eternal inflation, with an infinite multiverse that has always been inflating, then again we have an infinite regress with no ultimate origin. Some philosophers and scientists argue that an infinite regress is not a problem. Why must there be a first cause? Why can't the chain of causation extend infinitely into the past? In mathematics, we are comfortable with infinite sets and infinite sequences, and there is no logical contradiction in an infinite past. If the universe or multiverse is eternal, with no beginning, then there is no need to explain an ultimate origin. The question what existed before simply has an answer at every point. There was something before, and something before that, without end. Others argue that an infinite regress is philosophically unsatisfying or even incoherent. Philosopher William Lane Craig, for example, argues that an actual infinite cannot exist in reality, only as a mathematical abstraction. If the past were infinite, then an infinite number of events would have already occurred, which Craig argues is impossible. Moreover, if the universe had no beginning, then how did we arrive at the present moment? If there were infinitely many days before today, how did we traverse an infinite number of days to reach today? This argument, known as the Kalam cosmological argument, concludes that the universe must have had a beginning, a first moment in time. The argument is contentious. Critics point out that our intuitions about infinity, developed from finite experience, may not apply to the actual structure of time and causality. They also note that modern physics, particularly quantum mechanics and relativity, have already shown that our intuitions can be misleading. If physics suggests that the universe is eternal, or that time is an emergent phenomenon, then we should be willing to revise our philosophical assumptions rather than insisting that the universe conform to our intuitions. The question also intersects with the problem of the principle of sufficient reason, the idea that everything that exists must have a reason or explanation for its existence. If the universe as a whole has no explanation, if it just exists as a brute fact, then the principle of sufficient reason is violated, at least for the universe itself. Some philosophers, like Leibniz, find this unacceptable and argue that there must be an ultimate explanation which they identify with God. Others, like Bertrand Russell, argue that the universe is a brute fact and that the principle of sufficient reason does not apply to the totality of existence. In the context of modern cosmology, these debates take on new dimensions. If the universe emerged from a quantum fluctuation, or from a timeless quantum state, then there is a sense in which it has an explanation, the laws of quantum mechanics. But this raises the question of why those laws exist and why they have the form they do. If the universe is part of a multiverse, then its existence might be explained by the dynamics of the multiverse. But the multiverse itself requires explanation. We can always push the question back one level, and it is not clear that we ever reach a final, ultimate explanation that is itself unexplained. The future of cosmology and ultimate questions. As we look to the future, what can we expect from cosmology in the coming decades and centuries? Will we definitively answer the question of what existed before the Big Bang? Or will it remain forever beyond our reach? The answer depends on both technological progress and theoretical breakthroughs. On the technological side, the next generation of telescopes and detectors will provide unprecedented views of the early universe. The James Webb Space Telescope is already revolutionizing our understanding of the first galaxies. Future missions, like the Nancy Grace Roman Space Telescope and the proposed Habitable Worlds Observatory, will continue this work, mapping the universe in ever greater detail. Ground-based telescopes like the Extremely Large Telescope and the 30-meter telescope will complement these space missions, providing high-resolution observations of distant objects. Gravitational wave astronomy is still in its infancy, but it is poised for rapid growth. The LISA mission, scheduled for launch in the 2030 seconds, will detect gravitational waves from supermassive black hole mergers and potentially from the early universe. Future detectors, including proposed missions like the Big Bang Observer and the DC Hertz Interferometer Gravitational Wave Observatory, will push into new frequency ranges and increase sensitivity. The combination of electromagnetic and gravitational wave observations will create a multi-messenger view of the cosmos, revealing phenomena that are invisible to either method alone. Advances in particle physics will also contribute. The Large Hadron Collider continues to explore the high-energy frontier, and proposed future colliders, such as the International Linear Collider or the Future Circular Collider, will probe even higher energies. Discoveries of new particles or forces, or precise measurements of the Higgs boson and other known particles, will constrain models of the early universe and provide clues about the fundamental laws of physics. On the theoretical side, progress toward a complete theory of quantum gravity is essential. String theory, loop quantum gravity, and other approaches are maturing, and there is hope that within the next few decades, significant breakthroughs will occur. A complete theory would not only describe what happens at the Big Bang, but also make predictions that can be tested observationally. It might reveal new symmetries, new dimensions, or new principles that transform our understanding of space, time, and matter. Computational cosmology is also advancing rapidly. Modern supercomputers can simulate the evolution of the universe from the Big Bang to the present, modeling the formation of galaxies, the growth of structure, and the effects of dark matter and dark energy. These simulations are becoming more detailed and realistic, incorporating more physics and higher resolution. By comparing simulations to observations, cosmologists can test their theories and refine their models. In the future, simulations might even be able to model the pre-Big Bang phase, exploring different scenarios and predicting their observable consequences. Despite these advances, there are questions that might remain forever beyond the reach of empirical science. If the regions beyond our cosmic horizon are causally disconnected and will never become observable, then we cannot directly test theories about them. If the multiverse is real, and other universes are forever inaccessible, then we can infer their existence only indirectly through the theories that predict them. And if the ultimate laws of physics or the wave function of the universe are determined by principles that transcend observation, then we may never know them with certainty. This does not mean that the questions are meaningless or that we should stop asking them. Philosophy, mathematics, and theoretical physics can explore these questions even in the absence of direct empirical evidence. By developing coherent, mathematically precise theories, by comparing their predictions to whatever observations are available, and by using criteria like simplicity, elegance, and explanatory power, we can make progress even on questions that seem empirically inaccessible. The history of science is full of examples where theoretical ideas, initially speculative, were later confirmed by observations. The same might happen with theories about the pre-Big Bang state or the multiverse. Ultimately, the question of what existed before the Big Bang is one of the deepest we can ask. It pushes us to the limits of knowledge, challenges our assumptions about time and causality, and connects science with philosophy and theology in profound ways. Whether we ever find a definitive answer or not, the journey of exploration is immensely valuable. It expands our understanding, inspires wonder and curiosity, and reminds us of our place in the vast, ancient, and mysterious cosmos. The universe is calling us to understand its origins, and with the tools of modern science, we are answering that call, one discovery at a time. The human dimension of cosmic questions. Throughout this exploration of what existed before the Big Bang, we have focused primarily on scientific theories, mathematical frameworks, and observational evidence. But it is worth stepping back to consider the human dimension of these questions. Why do we, as finite beings living brief lives on a small planet, care so deeply about the ultimate origin of the universe? What drives us to ask questions about events that occurred billions of years ago, or about states that might have existed before time itself? And what does our quest to answer these questions tell us about ourselves and our place in the cosmos? The human drive to understand origins is ancient and universal. Every culture throughout history has developed creation myths, stories that explain how the world came to be and why it has the form it does. These myths serve multiple functions. They provide a sense of order and meaning, placing human existence within a larger narrative. They answer questions about identity and purpose, explaining who we are and why we are here. And they offer comfort in the face of the unknown, providing assurance that the world, despite its mysteries and dangers, has a comprehensible structure. Modern cosmology can be seen as a continuation of this ancient quest, using the methods of science rather than the language of myth. When we ask what existed before the Big Bang, we are asking a version of the same question that our ancestors asked when they wondered how the world began. The difference is that we now have telescopes, mathematics, and experimental methods that allow us to probe these questions empirically and to test our answers against observations. But the underlying motivation, the desire to understand our origins and our place in the cosmos, remains fundamentally human. This quest also reflects a deep-seated curiosity about the nature of reality itself. Humans are not content merely to describe what we observe. We want to understand why things are the way they are, to find the principles and patterns that underlie the diversity of phenomena. This drive for understanding has led to some of our greatest achievements, from the discovery of fire and the invention of agriculture to the development of mathematics, science, and technology. The question of what existed before the Big Bang is the ultimate expression of this drive, pushing our understanding to the very edge of what is conceivable. There is also an aesthetic dimension to these questions. The theories we have discussed, from cosmic inflation to the multiverse to loop quantum gravity, are not just intellectually interesting. They are also beautiful in a deep and abstract sense. The mathematics is elegant, the concepts are profound, and the implications are awe-inspiring. Scientists often speak of the beauty of a theory as a guide to truth, and while beauty alone is not sufficient to establish a theory, it is nonetheless a powerful motivator and a source of deep satisfaction. The quest to understand what existed before the Big Bang is, in part, a quest for this kind of beauty, for a theory that not only explains the data, but does so in a way that is simple, elegant, and profound. The question also has existential significance. Understanding where the universe came from, whether it had a beginning or is eternal, whether it is unique or one of many, shapes how we think about existence itself. If the universe emerged from nothing, or from a quantum fluctuation, it suggests that existence is, in some sense, contingent, that things could have been otherwise. If the universe is eternal, or part of an infinite multiverse, it suggests a different picture, one of endless diversity and possibility. These different visions of the cosmos can influence our sense of meaning and purpose, even if they do not determine it. For some, the scientific exploration of these questions is deeply fulfilling, providing a sense of connection to something greater than oneself. To study the cosmos, to trace the history of the universe from the Big Bang to the present, to contemplate what might have existed before, is to participate in the grandest narrative we know. It is to see ourselves as part of a vast, ancient, and ongoing story. A story that began billions of years ago and that will continue for billions of years into the future. This perspective can be humbling and inspiring in equal measure, reminding us of our smallness while also affirming our capacity to understand. For others, the same exploration might raise feelings of insignificance or existential angst. If the universe is vastly larger and older than we imagined, if we are just one tiny, fleeting phenomenon in an infinite multiverse, what does that say about the meaning of our lives? This question has been a recurring theme in philosophy and literature, particularly in the modern era as the scale and age of the universe have become clear. The 19th century philosopher Friedrich Nietzsche wrote about the death of God and the need to create new values in a universe devoid of inherent meaning. The 20th century existentialists, like Jean-Paul Sartre and Albert Camus, grappled with the implications of an indifferent cosmos and the need for humans to create their own meaning. Yet, as many thinkers have pointed out, the vastness and age of the universe do not necessarily diminish the significance of human life. Meaning is not determined by size or duration, but by the quality of experience, the depth of understanding, and the richness of relationships. A single human life, though brief and small in cosmic terms, can contain immense meaning, creativity, love, and discovery. The fact that we can ask questions about the origin of the universe, that we can develop theories and make observations to test them, is itself remarkable and meaningful. We are, in a sense, the universe becoming aware of itself, a part of the cosmos capable of reflecting on its own existence. This perspective is beautifully articulated by the physicist Carl Sagan, who wrote, "We are made of star stuff. We are a way for the cosmos to know itself." This idea that conscious beings like us are not separate from the universe, but are an integral part of it, provides a sense of connection and meaning that transcends questions of size or duration. The atoms in our bodies were forged in the cores of stars. The energy that powers our thoughts comes from the sun, and the patterns of our DNA were shaped by billions of years of evolution. We are deeply embedded in the cosmos, and our quest to understand it is a natural expression of our cosmic origins. The question of what existed before the Big Bang also invites us to think about the limits of knowledge and the nature of scientific inquiry. Science is extraordinarily powerful, capable of answering questions that once seemed unanswerable, but it also has limits. There are questions that may be empirically inaccessible, phenomena that cannot be observed even in principle, and aspects of reality that might forever elude our understanding. Recognizing these limits is not a sign of failure, but a mark of intellectual honesty. It reminds us that science is a human endeavor, constrained by our tools, our theories, and our position in the universe. At the same time, the history of science teaches us that what seems impossible today might become possible tomorrow. Time and again, scientists have found ways to probe questions that were thought to be beyond reach, using new instruments, new methods, and new ideas. The question of what existed before the Big Bang may seem unanswerable now, but future breakthroughs in theory and observation might provide answers, or they might reveal that the question itself needs to be reformulated in light of new insights into the nature of time, causality, and existence. The convergence of disciplines. One of the most fascinating aspects of the question, what existed before the Big Bang, is how it brings together multiple disciplines, each contributing its own perspective and tools. Cosmology, particle physics, mathematics, philosophy, and even theology all have something to contribute to the discussion. This convergence of disciplines is a hallmark of the most profound questions, which resist simple answers and require insights from many sources. Cosmology provides the observational framework, the data from telescopes and detectors that constrain our theories and guide our thinking. Without observations of the cosmic microwave background, the expansion of the universe, and the formation of structure, we would have no empirical basis for discussing the Big Bang or what preceded it. Cosmology also provides the theoretical framework of general relativity and the standard model of cosmology, which describe how the universe evolves and what conditions prevailed in the early moments. Particle physics contributes an understanding of the fundamental particles and forces that govern the behavior of matter and energy. The physics of the very early universe involves energies and densities far beyond anything we can produce in laboratories. But particle physics provides the principles and equations that describe how particles behave at these extreme conditions. The Higgs boson, for example, plays a crucial role in the early universe, and understanding its properties helps us understand the phase transitions and symmetry breaking that occurred shortly after the Big Bang. Mathematics is the language in which physical theories are formulated and tested. The equations of general relativity, quantum mechanics, string theory, and loop quantum gravity are all mathematical structures, and solving these equations, understanding their properties, and deriving their predictions requires sophisticated mathematical techniques. Mathematics also allows us to explore possibilities that go beyond direct observation, to consider counterfactual scenarios, and to probe the logical structure of physical law. In some sense, mathematics provides a window into the realm of the possible, revealing what could exist even if we cannot observe it directly. Philosophy brings conceptual clarity and critical analysis to the discussion. Philosophers ask questions about the meaning of terms like before, cause, existence, and nothing. They examine the assumptions underlying scientific theories and explore the implications of different answers. Philosophy also addresses the epistemological questions about what we can know and how we can know it, and the metaphysical questions about what exists and why. The question of what existed before the Big Bang is not just a scientific question, but also a philosophical one. And ignoring the philosophical dimensions would leave the discussion incomplete. Theology, though often seen as separate from science, also engages with these questions. Religious traditions have long grappled with the origin of the universe, the nature of time, and the relationship between the created world and the divine. Modern cosmology provides new contexts for these ancient questions, and theologians are actively engaged in dialogue with scientists about the implications of discoveries like the Big Bang and the multiverse. For some, science and religion are seen as complementary ways of understanding reality, each offering insights that the other cannot provide. For others, they are in tension or even conflict. But in either case, the theological perspective is part of the broader human conversation about origins, meaning, and existence. The convergence of these disciplines also creates opportunities for misunderstanding and miscommunication. Scientists, philosophers, and theologians often use the same words but mean different things, or they operate with different assumptions and standards of evidence. Bridging these gaps requires patience, humility, and a willingness to engage seriously with perspectives different from one's own. When done well, interdisciplinary dialogue can be extraordinarily fruitful, generating new ideas and deepening understanding. When done poorly, it can lead to confusion, frustration, and unproductive debates. One example of successful interdisciplinary engagement is the dialogue between cosmology and theology around the question of creation. Many theologians have embraced the Big Bang as consistent with the idea of a creation event, a moment when the universe came into being. Others have grappled with the implications of an eternal universe or a multiverse, exploring how these ideas might fit with traditional doctrines of creation and divine action. Scientists, for their part, have become more aware of the theological and philosophical dimensions of their work, recognizing that questions about the ultimate origin of the universe touch on issues that go beyond empirical science. Another example is the collaboration between physicists and philosophers on the interpretation of quantum mechanics and the nature of time. These are not just technical issues, but also conceptual ones, requiring careful analysis of what the mathematics means and what kinds of ontological commitments it entails. Philosophers bring tools for analyzing concepts and arguments, while physicists bring knowledge of the empirical constraints and the mathematical structure of theories. Together, they can make progress on questions that neither discipline could fully address alone.